other people are not following up, there are janitorial people will come up and clean up stuff. But that's possible. Okay, it's worthwhile to do. Okay, brief history of reasoning. Okay, that 450 BC, propositional logic, and then Aristotle, then Cardano, then Boole, then Frege, Wittgenstein, Gödel, Erbrand. You should know Erbrand, by the way. You probably never heard of Erbrand. Big guy. And then Davis Putnam and Robinson. That's at least the minimum history. Okay, and they all did those pieces. In the end, in 1965, Robinson wrote a practical first order resolution refutation procedure. And when that was done, there was humongous celebrations in the AI world. Basically, people thought AI as a problem is now solved because there is a theorem proof. All I need to do is write down what I know and let the theorem prover do its thing. This is what they told you in the prologue class, right? Unfortunately, it has its problems, but for a while at least, there was a humongous amount of celebration in AI that we figured out one of the biggest mathematical stumbling blocks, which is how to do first order logic theorem proving. Then everything I know, I just write it in first order logic, and the theorem prover will do the rest of the work. Okay? Okay, so truth in first order logic. So the next several minutes, we'll just basically give a bird's eye view about how resolution refutation works, and then begin. Okay. So truth in first order logic, remember that ground atomic sentences are proposition symbols in effect. Okay, and so in essence you can then talk about what are the words in which they are true, what are the words in which they are false, and you can talk about the notions of entailment pretty much the same way we talked about entailment for propositional logic. But before we go there, actually it turns out that that's the second step. The first step, the most obvious way people can think of truth for propositional first order logic is another big guy, Tarski. Tarskian interpretations. A Tarskian interpretation for a logical database basically says for every predicate in the first order logic database, here is a real world relation. For every constant, here is a real world object. Okay? For every function, here is a real world function. Now, if I am making a statement about a relation between some objects, I can check if it holds in the real world. If it holds in the real world, then in that real world, this statement is true. In essence, this is what we were playing with when we were talking about why we should write that University of Arizona smart people sentence in one way versus another way. Because you assumed that there is actually a real University of Arizona in the real world. There is a real person going to this real University of Arizona, and there is this notion of going relation, there is a notion of smart relation, and you essentially check whether this is all holding true in the real world. If so, then the sentence is true for your real world. But the problem, of course, is, so this is why it's called an interpretation, and a model is an interpretation where your sentences hold. This is what I'm saying? Imagine I have a real world scenario which is probably closer to real world, where let's say 1,000 people are going to University of Arizona and none of them are smart. So then the sentence, there exists somebody who is smart in the University of Arizona. That sentence just happens to be false in the real world. Okay? If you have a different real world where 10,000 people are going and 2 people are smart, then in that world the sentence is true. Now how many different worlds can I construct like this? I can construct different real worlds by just changing the mapping between predicate symbols and relations, constants and objects, functions and functions. They're just mind-numbingly too many interpretations. It's infinity, but it's too big an infinity. It's too cumbersome an infinity. Okay, so to give that same thing I was saying, imagine I was talking about these constants, King John, 2 UCB, predicates brother greater than function square root f log, etc. Then here is one Tarskian interpretation. These are the pictures of the real world people. Okay, and then I can give a different Tarskian interpretation. All I did is change the color of some of the people. That's a different real world. And you can see how many different real worlds I can come up with, different interpretations I can come up with. And for every interpretation, I need to check if my sentence is holding true in that interpretation. And the definition of entailment is still the same. If I have a database, and this is the set of interpretations where the database holds, and alpha holds in all those interpretations, then alpha is entailed. That's what we said for predicate logic, for prepositional logic. We'll say that again for first order logic. Except it's just constructing these kinds of interpretations is just painful. So you jump ahead and say, I will do the kind of propositional interpretations that I'm happier with. Okay? Where essentially what I'll do is, let's say I take a database like this. For all x, king x and greedy x implies single x, King John, greedy John, brother Richard John. Now, of course, I can instantiate the universal sentence in all possible words all possible ways, because John is a constant, Richard is a constant. Those are the only constants in my database right now. Right? So then I can write this as King John and greedy John implies single John. King Richard and greedy Richard implies single Richard. King John, greedy John, brother Richard. Do people see that this is basically equal to this? I just compiled. Compiled is first order logic thinking to this. Now can I do theorem proving on this? Of course I can do theorem proving on this. Because this is just, if you imagine that the parentheses are just caches, then they're just proposition names. Instead of saying king parenthesis begin John, king parenthesis and, I'll just say king dash John. It's a proposition name. Similarly, greedy dash Richard is another proposition name. This is just a propositional database. And you know how to deal with propositional theorem proving. You can call it, and it will tell you whether alpha is true or not. So in fact, in particular, I guess, what would you probably want to prove from something like this? You might want to prove that John is evil. And actually, John is evil follows from this statement. You can see that from English, and it will also be true from your propositional theorem proving. You will be able to prove that John is evil. Okay? If you understand this, you essentially understand how you will go about doing theorem proving on first order logic. Not do a few small technical issues that could maybe hundreds and hundreds of years figure out. Okay? So, to get here in essence, I went from the first order logic database to a propositional database. Right? And it turns out that you can call this, basically, you can think of this database in terms of what is called Herbrand interpretations. That's another name, Herbrand. If you take any logic course, you will hear a lot about that. Basically what Herbrand said is, you don't need to do the Tarskian interpretations, they are just too cumbersome. You can do these sort of propositional interpretations, and that's Herbrand interpretations. So what Herbrand interpretation has in a Cliff's Notes form is it has two parts, Herbrand universe, Herbrand base. Herbrand universe is all the constants in your current knowledge base, all ground functional terms. All ground functional terms. How many ground functional terms will there be? How many ground functional terms will there be? How many ground functional terms will there be? Infinite. That's why it's a universe. The moment you have a function, Herbrand universe becomes infinitely large. Think of Herbrand universe as generalized object reference. Those are all the addresses of objects that basically exist in the real world. Okay? If you have a function, then essentially it allows you to talk about infinitely many different addresses. Now here's one thing that those of you who are still following can keep in mind, that just because you can refer to infinite number of addresses doesn't mean that the real world has to have infinite number of objects. If you got this, again, pat yourself in the back like vigorously. Okay? Because in essence, all these infinite number of addresses can actually be talking about the same object. They're just many pointers to this object. Just like the Skolem function, this ability to refer to infinite number of locations is expressiveness. It's very much possible that all of them are referring to the same object. You allow for that. But you also allow for they actually referring to many different objects. Okay, so that's Herbrand universe. And so basically Herbrand universe allows you to build terms. Terms from the first order logic database. Now Herbrand base then says take every predicate and a predicate, let's say of n n-ary predicate, that means n arguments, then just pick n thingies from this universe, plug them in. That will be a ground atomic sentence. Right? It will be a ground atomic sentence. So the way you construct a ground atomic sentence is you take a predicate and you put a term referent inside. The term referents come from Herbrand universe. Those are only the terms that are available. So you just throw them in, then you get a new ground atomic sentence. That is your Herbrand base. Herbrand base is the set of all ground atomic sentences. Now let's look at the following thing. If the Herbrand universe has size n, then you have, let's say, a p number of predicates, each of them taking k arguments. Then the Herbrand base contains for each predicate, it has k places. K places. Each of these places can be n different things because there are n different terms in the universe. So this n times n times n, k times. So it will be n power k configuration of terms per predicate. There are p number of predicates. So the total size of the Herbrand base for a Herbrand universe with n terms will be p times n power k. Do people see this? So there is an exponential blow up for the base. From the universe to base, there will be an exponential blow up. This is assuming n is finite. As soon as you have a single function, n is infinite. Which means Herbrand universe is infinite. Which means Herbrand base is infinite. When there are no functions at all, you can still quantify. Do people realize that? You can have quantification even if there are no functions. That part of first order logic without functions is called predicate logic. Predicate logic can be compiled to a finite sized propositional knowledge database. Predicate logic is actually just like object-oriented programs. They can be compiled down to a finite sized assembly language program. The moment you throw in a function, you are now beyond that analogy. Because essentially, the first order logic statement cannot be compiled, the database cannot be compiled into any finite sized propositional database. It can only be compiled into an infinite sized database. And it's no fun doing theorem proving on infinite sized databases. If you remember that theorem proving involves search, taking any arbitrary two clauses and trying to resolve them. You will now have infinite number of clauses, and it can take a long time. Okay? Do people get this? Again, you can kind of understand why I was making such a big deal about functions. Long back when I started talking about first order logic being semi-decidable, I said that the monster you want to be worried about is functions. This is the reason. The moment you throw in a function, you have infinite number of object reference, which means there are infinite number of objects in the Heilbronn universe, which means the Heilbronn base is infinitely large. Now, why do I care about this? It turns out that for the finite size, if you want to prove a statement in the original first order logic database, it is equivalent to proving that statement in the compiled Heilbronn database. You get this? So I have just basically solved one problem by reducing it to another problem that I don't want to solve. Now somebody has to prove this. That's why Heilbronn is famous, because Heilbronn proved this. But Heilbronn actually proved it, something even bigger, essentially. And actually Heilbronn and people after him proved something even bigger, which is even when Heilbronn base is infinitely large, you can talk about the notion of the depth of a term. This additional notion of the depth of a term. A constant has depth 0. A function of constants has depth 1. A function of constants has depth 2. Function of 15 times constant is the depth 15. Right? So you can organize the terms in your universe in terms of the zero depth terms, which are just constants, 1 depth terms, which is constants with 1 application of function, 2 depth, up to 2 depth terms, which is constants, 1 application of function, 2 applications of function. So you sort of, still infinity, you sort of organize this infinity into this nice fashion. Then for each one of these depths, there is essentially a finite universe. So there is a finite base, finite Heilbronn base. So if you can prove your theorem in that finite Heilbronn base, then I can show that it will also hold in the original first order logic database. So this tells you a nice loopy procedure for proving any theorem. Start with depth 0, propositionalize the database, see if you can prove the theorem. If you can't, if you show that the theorem cannot be proved, then go to the depth up to 1, try to prove. This is like iterative deepening, depth first theorem proving. This, my friends, is essentially the collected wisdom of our ancestors up until 1950s. Okay, so in essence, Heilbronn in 1930 said, if a sentence alpha is entailed by a first order logic knowledge base, it is entailed by a finite subset of the propositional knowledge base, where the finite subset is essentially a depth k subset. So you start with depth 0, depth 1, depth 2, etc. And so there is n equal to 0 to infinity, create a propositional knowledge base by instantiating only up to depth n terms, and then see if alpha is entailed. If it is, then you are done. If not, you keep doing this. Now, how many people see this and say, that's why this is semi-decidable? Do you understand this? If the theorem was provable, unbeknownst to you, then there must exist some finite depth of the universe, Heilbronn universe, for which the propositional knowledge base would have proved the theorem. If the theorem wasn't provable, you will keep on going from n equal to 0 to infinity, not knowing when to stop. That's the semi-decidability. Okay? The last thing that I want to do is to show you very briefly that resolution can be done on this first order logic. And it looks almost similar to what we did. Okay. In particular, let me just go with. Okay, yeah. So one thing about resolution is basically it looks exactly the same way as before. You have clauses. A clause is what's called an atomic literal. So basically, in this case, a literal is an atomic sentence, not necessarily grammar, just an atomic sentence. So it can have variable names. Okay, and so the kind of resolution that you would do is things like happy x, alive x implies happy x, let's say. For all x, anybody who is alive is happy. Okay, and then you say alive raw, and you want to prove is happy raw. So I will take this, negate it, and say not happy raw. Now this doesn't look like a class. It will become a class if I say for all x, alive, not alive x, or happy x. Right? At this point I'll just drop the for all. And I'll assume that whenever there is a variable, it must have been universally quantified. If you're still awake, you should cry foul, saying what happened to the existential variables? But I took care of that. By the time I come up to this point, I would have got rid of existential variables and put column constants or column functions there. By this time, all that will be left would be universals. And I say, who the heck cares about universals? You just remove it and just write the variables and assume that they are implicitly universally quantified. So then what happens is I have not alive x or happy x and not happy raw. I can resolve this and this by saying x is raw. Think about it this way. That guy is saying happy x, everybody is happy. And I'm giving you one guy who is not happy, raw. So for x equal to raw, that becomes happy raw, not happy raw. At which point I get to write not alive x, not alive x, but except x equal to raw. That means not alive raw. At which point I will say not alive raw and alive raw, empty class. You see what I just did? So this idea, what I just did, where I said happy, not happy raw and happy x, and I said they can be made equal if you set x equal to raw. It has a fancy name for it, it's called unification. You can unify this sentence to that sentence if you have this mapping. And the whole point is the top sentence, because any variable that is left is universally quantified. So it must be true for everybody. So if I can give you one mapping for which it's not true, then resolution can be done. Another way of looking at it is that I could have avoided doing that if I actually propositionalized the knowledge base and wrote everything in terms of not alive, alive raw implies happy raw, alive Tom implies happy Tom, alive John implies happy John, etc. Then it will just be pure propositional resolution. But now I'm actually doing much better. So what I showed in the theorem is you can compile everything into propositional resolution. But what I'm doing here is without compilation, I'm actually doing the theorem proving by just doing unification. This idea of doing unification without compilation to propositional thing is called lifted inference. You are basically doing inference while keeping variables around. And lifted inference requires unification. So that involves me showing you two more things and then one funny joke and we get to go. So one is that I actually can convert any arbitrary propositional first order logic sentence into clausal form. I did that for that little example. Can I do it always? Yes. It turns out I can do the same set of things that I did before for propositional logic. For example, eliminate biconditionals and implications, move existential inward, negation inward. When you're doing negation inward, you have to know how to take negation over for all. It becomes there exists. How to take negation over there exists. It becomes for all. Okay? And then standardize the variables apart. So this is very important because if I say for all x and some part, and then for all y some part, for all x some part here, and then for all x some part here again, these two x's can be completely different variable names. So I standardize the variables apart. So I give a new variable name to every quantified variable. So you realize this, right? That for all x, happy x implies since x is identical to for all y, happy y implies since y. Right? So all I'm doing is making sure that every quantification is on a different named variable. Why is this important? Because I need to get rid of the existentials. And for that I need to know under which variable scope is this variable. So that brings me to this green stuff, which is essentially after you standardize the variables apart, you remove every existential variable and substitute for it a Skolem function, which is a new function name. With its arguments, all the variables which are to the left of it and are universally quantified. Now imagine the following thing. Suppose, do I need to do a separate special case for functions versus constants? Functions versus constants. Do you understand what I'm saying? No. Why? Because imagine I just have there exists x, happy x. So x would have to be written as Skolem function sk15 of all the variables which are to the left of it that are universally quantified. What are those variables? Nothing. So now I have a function sk15 of 0 variables. What is a function of 0 variables? It's a constant. Everything just falls through. It's all coming up Milhouse. Right? Everything just falls through. If you just say, I basically convert the existential variable to be a Skolem function of all the variables to the left of it which are universally quantified. If there are none, then it will become sk of 0 variables, which means it's a constant. Skolem constant is just a special case of Skolem functions. After you do that, you just drop universal quantifiers. At this point, I don't need universal quantifiers anymore. That's science. At that point, I distribute and over R and I just have CNF formulation. I realize I'm going faster on this. I'm basically trying to make you understand at some level, some gut level, that first order logic is essentially very similar to propositional logic inference with a couple of changes. One is this unification thing I talked about. The other is this formalization. So, two funny examples and we get to go. This shows the power of the first order logic theorem. Everyone is loved by someone. If x loves y, x will give a Valentine's card to y. Will anyone give Rao a Valentine card? Huge suspense. Right? Okay, so everyone is loved by someone. I will write it this way. For all x, there exists y, such that loves by x implies. This is the sentence. Everyone is loved by someone is this sentence. For all x, there exists y, loves by x. I could have written the opposite way, but I assume that when somebody says everybody is loved by somebody, they assume that that somebody is dependent on this everybody. Right? So that's why I write for all x there exists y rather than there exists y for all x. Okay. Then if x loves y, then x will give Valentine's card to y. For all x, for all y, loves by x implies gives Valentine's card yx. Things are getting sort of daytime soberness, right? Now, will anyone give Rao a Valentine's card? I want to say there exists Z such that Z gives Valentine's card to Rao. To prove that somebody will give me a Valentine's card, you essentially assume you're such a loser that there does not exist Z who will give you a Valentine's card. And then if you can get an empty class, then I get to say I am loved, somebody will give me a Valentine's card. Agreed? Right? Okay. So, now having done this part, the second part is converting every one of these into CNF classes. How do I convert this into CNF class? There is no implications, nothing. The only thing is I need to get rid of this existential variable. Y. Y is in the scope of x. So really I will just take Y and say it is sk of x dash being the new variable, the standardized variable. Standardized apart variable. So I will write this as loves sk x dash. And then I remove that for all part. So this looks just like my happy sentence, my CNF class. And then this again becomes not loves by x or gives Valentine's by x. And I remove the for all part. This, there does not exist Z such that GV is Z Ra. Avoid the temptation of solemnizing right away. First pull the negation in. If you pull the negation in, it becomes for all Z, not GV Z Ra. At this point, if you have any solemnization to do, you do. It's important to remember that you do solemnization after you pulling the negations in. That's what we said in the procedure. So then, this is essentially not GV Z Ra. Okay, so let me see if I can prove anything here. So I can resolve not GV Z Ra to not logs by x GV by x. If I can make this guy be equal to this guy without the negation sign, then I can resolve them away. Right? I can make that if I make y equal to z and x equal to Ra. You can see this, it's very easy. This is the unification step. You can write a little algorithm for doing the unification, but for this particular example, you can very easily see it. Right? So if I can make z to be y, and y to be z and x to be Ra, then both of them become GV Z Ra. At which point I can remove both of them, and then I will get not logs by x, except this y would be z and this x would be Ra. The same substitution I did earlier, I have to do it again.